Okay guys, so this bonding basically just takes place when atoms share electrons. They're trying to achieve noble gas electron configuration or perfect octet. This is an energy lowering process, or exothermic if you're looking at reactions, pretty much. Now covalent bonds form between one or more nonmetals. No metals, that's ionic, no transition metals. These are directional bonds that create molecules with definite shape. Now the directional portion basically just means that molecules form. Now this whole thing is the opposite of ionic bonds, so that's important to remember. Bond polarity. Since electrons are normally not equally shared among atoms in a covalent bond, bond polarity is seen to the uneven pull of electrons. So electronegativity is what basically helps you find bond polarity. It's the ability of an atom to attract electrons to itself in a bond. Now polarity is determined by finding the difference of electronegativities between atoms. These numbers can be found on an electronegativity value chart. It's pretty simple, just like the pretty rainbow one that I have found for you guys. You can find exact numbers on that, or you can basically just predict bond polarity, which is pretty simple too if you know how to use the electronegativity periodic trend, where you go right across the periodic table, the En numbers increase, and if you go up a group, they increase. So fluorine has the highest. Now using exact numbers. Now if you have a delta En 0 to 0.5, then it's always nonpolar. Your molecule is nonpolar. If you have delta En 0.5 to 1.7, molecule is always polar. And any difference greater than 1.8 is always ionic, so it has nothing to do with any of this covalent crap. Intermolecular forces are seen when molecules are polar or nonpolar. They're summed up as the attraction between atoms in a bond, and they're basically based on attraction strength, but these aren't the bonds, these are just attractions. Now, polar covalent. This results from a permanent dipole moment where one side of the molecule is slightly positive and the other is slightly negative due to a greater electron pull. This is a function of shape or molecular geometry. These are only soluble in polar solvents, like dissolves like, remember? Now, types of IMFs. For polar covalent, you have two. First is dipole-dipole. This is the second strongest IMF of all three. The size of the permanent dipole moment will determine the strength of this IMF, so you have a greater dipole moment, there's more attraction, stronger IMF. Boiling point can also be determined and compared based on the size of the dipole. If you have a larger dipole moment, there's going to be more of a pull-off from the negative side, and your IMF is going to increase. If you have a higher IMF, you need more energy to boil your molecules or help them to vaporize. So you need more energy put in, your boiling point's going to increase. Same way for opposite. Now, 2 would be hydrogen bonds. That's the second type of IMF. This is the strongest IMF. Now, there must be a hydrogen bonded to an oxygen, nitrogen, or fluorine, HNOF is how we remember that, for it to be a hydrogen bond. There are no exceptions, people. Now, just remember that this always increases boiling and melting points due to attraction strength. This is the strongest IMF, and if you have stronger IMFs, you're going to need more energy to overcome them. So, to boil or melt things with molecules, you're going to need more energy put in to overcome those attractions. Nonpolar covalent results from a temporary dipole that can sometimes be induced. These are only soluble in nonpolar solvents, unless your molecules can hydrogen bond with water, and that's really the only exception. Now, mass and surface area are greater in nonpolar molecules because there's not an uneven pull of electrons, so mass is distributed where it needs to be, and there's a neutral charge overall. There's one type of IMF for nonpolar, London dispersion or van der Waals. This is the weakest IMF and has the lowest boiling and melting points of molecules because there's less attraction. Pretty much opposite concept of hydrogen bonding. Less energy needed to overcome the IMF, so boiling and melting points will go down. Alrighty, Lewis structures. These are pretty simple, but just basically a visual way to depict covalent bonding among atoms. These can be drawn using certain symbols and just following a couple simple guidelines. Start by knowing your central atom, and if there's a carbon, it's always a central atom. You have to write all the elemental symbols involved in the proper molecular shape or arrangement based on the amount of ligands and lone pairs. Count the number of valence electrons, we all know that. The bonding pairs are what's important. These are the electrons shared between atoms. One pair of electrons are shown as one single dash. Now, the bonds. Single bonds are 1 dash, double bonds 2 dashes, and triple bonds 3 dashes. We all know that. We're not really that dumb. Now, lone pairs, or electron pairs that do not bond between atoms, are shown as 2 dots next to the element symbol for the element which they belong to. Now, you have to have them in pairs because electrons can't come by themselves. I like to pretend that they like having friends, so just think of it that way, that electrons like to have friends, so they always come in pairs. I have 2 examples. On the left, boron trifluoride. This is a nonpolar molecule because there's no uneven pull. All the electrons are distributed where they need to be, and all atoms are happy with the electrons they have. Xenon tetrafluoride, on the other hand, has two lone pairs on xenon, which has a negative pull in opposite directions, which affects the geometry, and this is polar. Resonance and formal charge. Resonance structures are basically just bonded molecules, but with more than one valid Lewis dot structure, and those are the resonance structures, or otherwise called isomers. So, some resonance structures for a molecule can be valid but not equal to the original molecule. So in this case, the most stable molecule is the one chosen to represent the bonding. Formal charges are real simple, can be used to determine which structure among isomers is most stable and valid to represent a molecule. It's just the charge an atom would show when all of its bonds are perfectly covalent. If the sum of all formal charges for each atom in the molecule structure equals 0, then that is the most stable structural isomer. And if the overall formal charge sum of all atoms is greater than 0, then there's a lack of electrons. So it's going to be more positive. If the overall formal charge is less than 0, then there are too many electrons, and it's going to be negative. I just have a quick example right here. I'm not going to run through the whole thing. It's basically just two resonance structures. A double bond has shifted, and the one on the right is the more stable one due to formal charges that I found. Basically, just the carbons are more stable and are perfectly happy with the amount of electrons they have due to the double bond. Okay, now example. Basically, this problem is just saying to draw Lewis structures and 3 resonance structures for nitric acid, and then use formal charges to find which is most valid and stable. Alright, so I have a sample photograph here. Now the shifting double bond moves between the nitrogen atom and the oxygen atoms. We can see that. The above structures are only 2 of 3 structures. The third resonance structure would contain the double bond on the bottom right-hand side between the nitrogen and the oxygen bonded with the hydrogen. This is just really a photo to use an example showing how the bond is moving around. So the resonance structure that would be most accurate would be really none of these structures. And I found this because the nitrogen atom is always going to have 4 electrons due to the double bond giving it a formal charge of 1+. Throughout all 3 structures, 2 of the oxygen atoms, including the double bonded one, will have formal charges of 0 and will be stable, but 1 oxygen will have a negative end and have 7 electrons when it wants 6, giving it a formal charge of 1-. There's a total of 24 valence electrons, and when you draw all the resonance structures out like it did, they're really all equal, just the double bond is shifting around, making different oxygens have a formal charge of 1-, and then obviously the hydrogen atom isn't affected, it remains at a formal charge of 0. Alright guys, so that is my presentation. I know it was long, but I hope you liked it, and I love you all.